Good evening,
Hello,
sir. You can start now, sir.
yes, ma'am. Welcome back. Some of the questions in the next test paper. First question is, hello. All right. Welcome. Yesterday we were learning the synopsis of topic electrochemistry. Today we will learn the synopsis of the topic chemical kinetics, and then we will continue the questions in later stages. Now, the chapter what we're learning is chemical kinetics. Chemical kinetics. Now, this chemical refers to reactions and kinetic refers to rate. This rate is also called as velocity. This velocity also is called as speed. So chemical kinetics is a branch in chemistry which deals with the study of the speed of a chemical reaction, the rate of a chemical reactions, rate of chemical reactions. Not only the rate of chemical reaction, we also study mechanism of the chemical reaction, because reaction do not take place in one step. If the reaction takes place in many more steps, we need to know the mechanism of the reaction. Therefore, this chemical kinetics is a branch in chemistry which deals with the study of rate of a chemical reaction as well as the mechanism of the chemical reaction. Now, in this chapter, chemical kinetics, we say as a rate of a chemical reaction, we understand how fast the reaction can proceed, what's the path in which the reaction takes place, how far the reaction happens, to what extent the reaction takes place, whether the reaction is reversible or irreversible. All this can be learned under the topic called as chemical kinetics. So chemical kinetics provides an answer for all these questions. That is, how slow or fast the reaction is, what is the path or the mechanism of the reaction, whether the reaction is reversible or irreversible. All that is answered by chemical kinetics chapter. And we also can learn or predict the feasibility of the reaction. Feasibility of the reaction can also be learned from the chapter chemical kinetics by using Gibbs free energy concept. Delta G is equal to delta H minus T into delta S. Based on this, this is a thermodynamic factor which predicts whether the reaction, which predicts the reaction to be spontaneous or non-spontaneous. Now, just for your information, if delta G is negative, free energy is negative, the reaction is spontaneous. If delta G is positive, the reaction is non-spontaneous. And if delta G is equal to 0, the reaction is in equilibrium. So based on these, in this introduction, we will talk about the topic chemical kinetics. Now, many chemical reactions are spontaneous. Spontaneous means a reaction which happens by itself without the help of any agency. Those are called as spontaneous reactions. And these spontaneous reactions are unidirectional. That means it's irreversible. It's happening on only one direction. However, the reactions may be fast or slow. Based on the speed, they are classified into 3 different types. One is very fast reactions. These very fast reactions are called as instantaneous reactions. Instantaneous reaction. Very fast reactions are instantaneous reaction. This instantaneous reaction takes place with the time 10 to the power minus 16 to 10 to the power minus 14 seconds. 10 to the power minus 16 to minus 14. See, the reaction is very, very fast. In the blink of an eye, the reaction can take place. These reactions are called as very fast reactions. And they are also called as instantaneous reactions. Now, generally, these very fast reactions are instantaneous or ionic reaction or inorganic reactions. Generally, ionic reactions are very fast. Not only ionic reactions are very fast. So, example, now if you take a sulfate radical, to check the sulfate radical, we will add barium chloride solution. When we add barium chloride solution, as soon as the barium chloride comes into contact with sulfate, a white precipitate of barium sulfate is formed. The formation of this white precipitate takes place very fast, in a fraction of a second. Therefore, this reaction is called as instantaneous reaction, very fast reactions. Likewise, maybe the second example, if we have to give neutralization reaction, acid and a base reacts to form salt and water. It is also a spontaneous reaction, and it's also very fast reactions. Generally, ionic reactions are very fast reactions. Inorganic reactions are very fast reactions, and they are called as instantaneous reaction. The second one, what we have is very slow reactions. Now, when we say very slow reactions, all right, some of the examples for very slow reactions. These reactions are very slow. We cannot determine the rate. Even for the fast reaction, we cannot determine the rate because the time is 10 to the power minus 16 to 10 to the power minus 14 seconds. Since it's very fast, we cannot determine the rate. Likewise, for very slow reaction also, we cannot determine the speed or we cannot determine the rate because it is very, very slow. And Nobody is interested in very slow reaction. I'll give you an example for the slow reaction, then you will know. A rusting of iron. Rusting of iron is a slow reaction. Rusting of iron is a very slow reaction. It takes months together. It takes almost years together also sometimes. So very, very slow reactions are a lot of interest. So we cannot determine the rate of the reaction. The third set of reaction we have is called as moderate speed reaction. Moderate speed reaction. Now for an example, moderate speed reaction, a high decomposition of hydrogen peroxide, decomposition of hydrogen peroxide. This H2O2 will decompose to form water and liberating oxygen gas. This reaction is a moderate speed reaction. When this reaction, we say it is a moderate speed reaction, it is not too fast or too slow. The reaction is between the first two categories. In this type reactions, we can measure the rates of the reactions. And these kind of reactions, wherein we study the rate as well as we can study the mechanism of the reaction. All right. Next, we have to understand what is a chemical reaction. What is the rate of a chemical reaction? We will learn the rate of a chemical reaction in 1 minute, a few minutes time. Now, coming to the rate of reaction, we define rate of a reaction as ratio of change in concentration with respect to change in time. Change in concentration with respect to change in time. Now, we will learn this rate of reaction using a graph also. All that I'll teach you today, and we're going to learn few important questions based on important formulas we will see. Now, coming to the rate of a reaction. Rate of a reaction is generally represented by small letter r. It is defined as the ratio of change in concentration with respect to change in time. The ratio of change in concentration with respect to change in time is called as the rate of a reaction. Now if you consider a reaction, R giving you product. R is the reactant and P is a product. Now we can define rate of a reaction with respect to reactant as well as the product. As the reaction proceeds, the concentration of the reactant will decrease and the concentration of the product will increase. Now, if there is no change in the concentration of the reactant or the product, it means the reaction is not taking place. Now, how do we define rate of reaction? Rate of a reaction with respect to reactants. With respect to reactants, I told you the concentration of the reactant has to decrease. So it is decrease in concentration of the reactant with respect to time. Now, rate of reaction with respect to reactant is defined as decrease in concentration of the reactant with respect to time. That's why we represent minus sign. Now, if you plot a graph like this is concentration of the reactant, and this is with respect to time. At time t is equal to 0, no reactions are proceeded, the concentration is maximum. As time proceeds, the concentration of the reactant keeps on decreasing. The slope of a slope will give you the rate of a reaction. This is change in concentration and this is change in time. So change in concentration, we can represent as delta C by delta T. Change in concentration with respect to time. Since we're talking about reactant, we can represent as what? Delta R, change in concentration of reactant with respect to change in time. And this will be in minus sign. Why it is in minus sign? It's because the concentration of reactant decreases. Similarly, rate of reaction with respect to products. With respect to products, the concentration of the reactant products increases. The concentration of the product increases. So increase in concentration of the product with respect to time. So this is how we define rate of reaction with respect to product. So if you plot a graph, this is concentration of the product with respect to time. At time t is equal to 0, the concentration of product is 0. As time proceeds, concentration of product keeps on increasing. The slope of this also, will give you the rate. Slope will give you the rate, and that will be equal to change in concentration of the product with respect to change in time. We have not written a minus sign because product has to increase. The concentration of the product will increase. This is how. Now, what is the unit for rate of the reaction? Unit for rate of the reaction is change in concentration. Concentration is mole per decimeter cube, molarity. And time normally we take in seconds. Mole per decimeter cube per second is the unit for rate of a reaction. Now, coming to the next concepts. The next concept, what is important is reaction rate and stoichiometry. I think I taught you in some of the questions also yesterday or in the previous class, I taught you what's the relation between reaction rate and stoichiometry. Now, firstly, we need to know how to write the reaction rate and stoichiometry so that we can work one or two problems to do now and continue with the next concepts now. Now, for a simple example, like ammonia, synthesis of ammonia, nitrogen and hydrogen, giving you 2 NH3. This is the reaction. All are in gaseous state. Now, what is the reaction rate and stoichiometry relation? Now, rate is equal to change in concentration of nitrogen minus. Why minus? Nitrogen is a reactant. Change in concentration of nitrogen with respect to change in time. That will be equal to change in concentration of hydrogen with respect to time. But for hydrogen, you can see the coefficient is 3. Since the coefficient for hydrogen is 3, we have to divide it by 3. And we'll have to give a minus sign because this hydrogen is also a reactant. That will be equal to plus 1 by 2 because the coefficient of ammonia is 2. Ammonia is a product. Change in concentration of ammonia with respect to time. This kind of relationship is called as the reaction rate and stoichiometry. The rate of a reaction may be expressed in terms of rate of appearance of product or disappearance of the reactants. So this relationship is called as reaction rate and stoichiometry. Now we will take one more example, a simple example, like 2 moles of dinitrogen pentoxide on heating, it decomposes for dinitrogen tetroxide and oxygen gas. Now, what will be the reaction rate and stoichiometry? Rate will be equal to minus change in concentration of N2O5 with respect to change in time. But the coefficient is 2, so you have divided by 2, minus 1 by 2, change in concentration of N2O5 with respect to time. That will be equal to plus 1 by 2 delta N2O4 with respect to delta T. That will be equal to change in concentration of oxygen with respect to here the coefficient is 1. So if we divided it by 1 also, it makes no difference. Based on this, problems are important. One simple problem we will learn, and then we'll continue with the next concept. The question is this, right? In an experiment on catalytic oxidation, 4NH3 plus 5O2 giving you 4NO plus 6H2O. The rate of formation of NO was found to be 2.4 into 10 to the power minus 3 mole per liter per second. Calculate, under that they've asked two questions. First one is rate of disappearance of ammonia. Rate of disappearance of ammonia. The second question they've asked is rate of formation of water. Rate of formation of water. Now we will answer this question. Firstly, we need to write the relationship, reaction rate, and the rate at which the reactant disappear, and the rate at which the products are formed. The stoichiometric relationship between reaction rate to write. So we will write it here. Now the reaction they've given us. The reaction they've given is 4NH3 plus 5O2 giving you 4NO plus 6H2. What will be the rate? Rate will be minus 1 by 4. Change in concentration of ammonia with respect to time. That will be equal to minus 1 by 5. Change in concentration of oxygen with respect to time. That will be equal to plus 1 by 4. Change in concentration of NO with respect to time. That will be equal to plus 1 by 6. Change in concentration of water with respect to time. What is that they've given in the question? They've given the rate of formation of NO. That means they've given change in concentration of NO with respect to time. It's given. What's the value they're given? It's given as 2.4 into 10 to the power minus 3. This is what moles per liter per second. And they're asking you the rate of disappearance of ammonia, first question. So what we can do is we can equate these two equations. When you equate these two equations, we can write minus 1 by 4 change in concentration of ammonia with respect to time will be equal to plus 1 by 4 change in concentration of NO with respect to time. So if we take this 4 to the right side, so that will be what? Rearranging the term. So this 4 and this 4 will get cancelled. So change in concentration of ammonia with respect to time minus sign will be equal to change in concentration of NO with respect to time. That will be equal to 2.4 into 10 to the power minus 3 because it's equal. The stoichiometric rate equations are equal. This is the first one. The second part is that this rate of disappearance of ammonia is equal to rate of formation of nitric oxide. That is what it means. The second step, they're asking you to calculate a formation of water. So in order to understand the rate of formation of water, these two equations we will equate. So when we equate, it's plus 1 by 4 change in concentration of NO with respect to time will be equal to plus 1 by 6 change in concentration of water with respect to time. Since we want the concentration of water, change in concentration of water with respect to time, the 6 can be taken here. It will be 6 by 4 times change in concentration of NO with respect to time. That is 6 by 4 into They were given concentration of NO 2.4 into 10 to the power minus 3. On simplification, the answer we will get is 3.6 into 10 to the power minus 3 mole per liter per second. This is the relationship. These kind of problems they're asking, they will ask it for 1 mark, and you should take time so that you can solve this problem in a minute. So you cannot take time as I'm doing. You should be quick to answer these questions for your competitive exams. So I hope that you followed how to write the relationship between rate of formation and also rate of disappearance of the reactant. Rate of formation of the product and rate of disappearance of the reactant. Now, coming to the next concepts, law of mass action. Law of mass action. This law of mass action is proposed by Goldberg and Veitch, name of the scientist. It's theoretical. If A moles of A plus B moles of B giving you product, then the rate of a reaction is directly proportional to the product of molar concentration of reactants whose coefficients are raised to their power. Now, this is law of mass action. In order to define law of mass action, the temperature to be constant. The condition is at constant temperature, the rate of a reaction is directly proportional to product. Product means multiplication. Product of square brackets indicates molar concentration. Molar concentrations of the reactants whose coefficients are raised to the power. A and B are the reactant. A is the stoichiometric coefficient A, and B, smaller b, is the stoichiometric coefficient of B. So, according to law of mass action, we understand rate of a reaction is directly proportional to product of active masses of the reactants whose coefficients are raised to the power. Now, if we remove the proportionality sign, we give a proportionality constant K, and that proportionality constant K is called as rate constant, where K is equal to rate constant, or it is also called as velocity constant. It's also called as velocity constant. Now, for the same reaction equation, if the concentration of A is same as the concentration of B, and it is taken as unity. Unity means 1 molar. So what happens? R will be equal to K into 1 to the power A and 1 to the power B. So 1 to the power anything will be 1. Therefore, rate becomes equal to K. So rate of the reaction becomes equal to rate constant of the reaction when the concentration of the reactants are taken as unity. When the concentration of the reactants are taken as unity. Since the reactant concentration is taken as unity, the rate of a reaction becomes equal to the rate constant of a reaction. So remember. Now, what's the unit for rate of a reaction? We learned it in the previous video. It is mole per liter per second. Now, coming to the other concepts. The other concepts is factors influencing the rate of a reaction. See, this in this equation, applying law of mass action, this law of mass action is based on the law. It is theoretical. So we cannot determine the rate of a reaction theoretically. So we have to determine the rate of a reaction by experimental ways. So when we determine the rate of a reaction experimentally, then the relationship between the rate and the concentration of the reactant in an experimentally determined rate equation is called as a rate law, or it is called as rate expression. Now, what are the factors influencing the rate of a reaction? Factors influencing the rate of reaction. The first factor is concentration increases, the rate of reaction also increases. Now, more the concentration, greater will be the number of collisions. More frequent will be the collisions. So concentration, first factor, concentration, more is the frequency of collision. Therefore, products can be formed more. Therefore, the rate of reaction increase. The second factor is temperature. As temperature increases, reactant molecules will gain more kinetic energy, and they can move with high speed, and they can also collide more with high energy. Therefore, reaction can be formed. The third factor influencing the rate of reaction is the surface area. Greater the surface area, the reaction is also faster. The fourth factor is catalyst. The presence of catalyst increases the rate of reaction. Presence of inhibitor, opposite of catalyst, inhibitor, slows down the rate of reaction. Catalyst will increase the rate of reaction. Inhibitor will decrease the rate of reaction. Fifth one, it is nature of the reactants. Nature of the reactants. So in case of the nature of the reactant, it's a common experience. Inorganic reactions are very fast, while organic reactions are slow. This is because in inorganic reactions, ionic in nature. In organic reactions, the molecules are covalent. Further, since it is covalent molecules, and the orientation of the molecules may also matter. So bonds, the old bonds have to break, the new bonds have form, all that. So therefore, generally organic reactions are slow. So nature of the reactants. Ionic reactions are fast, molecular reactants are slow. Next is presence of light. Presence of light. Certain photochemical reactions. So reactions, chemical reaction which happens only in the presence of sunlight will be called as photochemical reactions. So photochemical reactions requires light. So they do not react, or a photochemical reaction do not take place in dark. So they happen only in the presence of light and energy. So these are the 6 factors which influences the rate of a reaction. One is concentration, temperature, surface area, catalyst, nature of the reactants, and also the presence of light. So these are the factors which influence the rate of the reaction. Now coming to the next concept, that is the formula. I'll give you the formula so that we can work few problems. Now, how do we find the rate of, now before that, we need to understand the term called as order of the reaction. Now, order of the reaction is sum of the powers of concentration terms in an experimentally determined rate equation. Determined rate equation. So order of the reaction is defined as sum of the powers of the concentration terms in an experimentally determined rate equation. See, this experimentally determined rate equation is called as rate law, or it is called as rate equation. Rate law, or it is called as rate equation. So in the rate equation, now for an example, if we take A moles of A and B moles of B, giving you product. So according to law of mass action, a rate is directly proportional to concentration of A to the power A and B to the power B. Or we can write this as a rate is equal to K into concentration of A to the power A into B to the power B. Now, same reaction if you perform experiment and determine the rate. So rate is directly proportional to concentration of A to the power P and concentration of B to the power Q. So this A and B are called as stoichiometric coefficients. Here P and Q are called as actual coefficients, which is determined by the rate. So R will be equal to K into A to the power P into B to the power Q. Now A plus B may be or may not be equal to P plus Q. There is no condition that A plus B is always equal to P plus Q. It may be or may not be equal to the actual coefficient. There is a stoichiometric coefficient, there is actual coefficient. Now we're talking about the order. So this order is some of the powers of the concentration terms in an experimentally determined rate equation. So in this equation, the sum of the powers is called as order. So we'll not talk about theoretical way. So in case of this, the order of this particular reaction is P plus Q. This P plus Q may be equal to A plus B or may not be equal to A plus B. Now, based on this, we have different types of orders: zero order reaction, first order reaction, second order reaction, all that. Pseudo unimolecular reaction, fractional order reaction, so many other reactions. Now, what is the unit for a rate constant? First, we will try to understand the unit for rate constant for different order reaction. For different order reaction. Unit for rate constant for a different order reaction. For a different order reaction, the rate constant can be calculated by a general representation. The unit for rate constant K can be given by one by time, or maybe we can write as general rate constant K can be given by the formula concentration to the power 1 minus n into per time. Now, for a zero order reaction, zero order reaction, n is equal to 0. When n is the concentration, generally it's mole per liter or mole per liter. So it will be K will be equal to mole per liter. It's mole per liter to the power 1 minus 0 per time. Time is normally in seconds. Second is S. So it will be mole per liter per second. This will be the unit for a zero order reaction. For a first order reaction, n will be equal to 1. When n is equal to 1, what will happen? K for rate constant for a first order reaction, it will be mole per liter to the power 1 minus 1, because n is 1 here, and per time. N 1 minus 1 is 0. Anything to the power 0 is 1. Therefore, per second. The unit for rate constant of a first order reaction is only per second. Similarly, what is the rate constant for a second order reaction? For a second order reaction, unit is mole per liter to the power 1 minus 2 per second. So it will be mole per liter to the power minus 1 per second. So it will be liter per mole per second. This will be unit for a second order reaction. So these kind of questions they can ask, what is the unit for first order, second order reaction? Likewise, molecularity, number of reactant molecules taking part in the elementary reaction. So we are not going to talk about the molecularity now. Formulas I will give you, and we'll work one or two problems based on those formulas. Yeah. Now, coming to the formula for a zero order reaction. For a zero order reaction, you should remember Now for a zero order reaction, a rate constant is equal to x by t. Rate constant is x by t. Now x is molar concentration and t is time. So it will be mole per liter per seconds. X is the initial concentration and t is the time. So this is the relation for zero order reaction. Now, how is half-life related to the zero order reaction? Rate constant, half-life. Half-life is represented as T 50%, or T half. So K will be equal to X by T, or T is equal to X by K. So at half time, X is equal to A by 2. So T half becomes equal to, this is T half. At half-life time, X is A by 2, T becomes T half, 50% time. So T half is equal to A by 2 divided by K, or T half is equal to A by 2K. This is the relationship. Or maybe we can write this T half is equal to initial concentration. We write as A naught by 2K. This is for zero order reaction. This is the rate constant expression, as well as this is the relation between rate constant and the half-life. Now for a first order reaction, rate constant K is equal to 2.303 by T log to the base 10 of concentration of the reactants R naught at time T is equal to 0. That is initial concentration, and R concentration after some time T. This is the relation between rate constant and concentration for a first order reaction in aqueous medium or in solution state. In gaseous state, K will be equal to 2.303 by T log to the base 10 of P naught minus 2 into P naught minus PT. P naught is initial pressure and PT is the pressure after certain amount of time. This is the formula for a first order reaction in gaseous state. Now, what's the relation between first order reaction and half-life period? This relation we know K is equal to 0.693 by T half, or we write it as T half is equal to 0.693 by K. These are the formulas which we should know. In case of radioactive decay, this radioactive decay, we write it as T half is equal to 0.693 by lambda. Lambda is called as disintegrations. So this is the relation for radioactive substances. And we also have, we write this for radioactive substance K, we can write it as, not K, we write it as lambda is equal to 2.303 by T log of N naught by N. It's NT. Number of atoms, time T is equal to 0, and number of atoms after time T is equal to 0. Coming to the questions, we'll solve one or two questions and we'll see. Now coming to the problem, few problems we will solve. So first problem is this. The first order, maybe I'll give you this one, T half. No, not this. T half of a reaction, A giving you product, is 1 hour. T half for a reaction, A giving you product is 1 hour. When the initial concentration of the reactant A is 2.0 mole per liter, how much time it takes for its concentration to come from 0.5 to 0.25 mole per liter if it is a zero order reaction. If it is a zero order reaction. T off of a reaction is given 1 hour. When the initial concentration of reactant is A is 2 mole per liter, how much their time it takes for it to come to from 0.5 to 0.25 mole per liter if it's a zero order reaction. For a zero order reaction, we know solution. For a zero order reaction, T half is equal to A by 2K. T half is 1 hour. That is equal to initial concentration is 2.0 divided by 2K. So K will be equal to 1 mole per liter per hour. We can simplify this. This will get cancelled. So K will be equal to 1 mole per liter per hour. Now, for a zero order reaction, for a zero order reaction, we also know that, right? We can write K is equal to A by 2 into T half. It's a cross multiplication. So K is 1.0. That is equal to, they're asking how much time is taken for its concentration to come from 0.5 to 0.25. So 2.25 mole, 50% reaction is 0.5 divided by 2 into T. So T half for this reaction is 0.25 hours. 0.25 hours. The next problem, this is based on zero order reaction only we are learning. The next problem is 50% of a reaction. 50% of a reaction was completed in 50 minutes. 50% of the reaction is completed in 50 minutes. The reaction was found. The reaction was found to complete in 100 minutes. What is the order of the reaction? What is the order of the reaction? Now, 50% of the reaction is complete in 50 minutes. And they've given 100% of the reaction is complete in 100 minutes. 100 minutes, sorry. 100 minutes. Therefore, the reaction belongs to zero order. Reaction belongs to zero order. For a zero order reaction, K is equal to x by t. X is 50 and time is also 50, and x by t for the second case, x is 100 and time is also 100 in the second case, therefore it is 1. Here also it is 1, therefore it belongs to the zero order reaction. Now, the rate of first order reaction. The rate of first order reaction is 1.5 into 10 to the power minus 2 mole per liter per minute. At 0.5 molar concentration, of the reactant, 0.5 molar concentration of the reactant, calculate the half-life of the reaction. Calculate the half-life of the reaction. So we know that for a first order reaction, T half is equal to 0.693 by K. Now, what is K? Rate constant. Rate of a reaction is equal to rate constant into concentration. So what is rate constant? Rate constant will be equal to rate by concentration. Rate they have given 1.5 into 10 to the power minus 2. Concentration they've given us 0.5. That will be equal to 10 to the minus 2. That will be equal to 0.03 per minute. So half-life period is 0.693 by 0.03. That will be equal to 23.1 minute. 23.1 minute. So these kind of questions can be asked in your exam. So we'll continue further based on chemical kinetics in the next class, or we'll see whether we can solve some of the question papers. Thank you.